I guess we can start. As usual, let's start with a very brief recap of what we have learned in the last lecture. So last week we talked about recurrent neural networks, right? And we start from the very, very simple example of autoregressive model. So this is a autoregressive model without any latent variable, and we say that a typical example to use an autoregressive model is to model languages, because in languages you can model the conditional probability of the next word given all previous words. And you have 1 gram, 2 gram, 3 gram model that corresponds to a different order of Markov assumptions. And fast forward to the latent version of autoregressive model, we say that RNN, or recurrent neural networks, are actually latent version of this autoregressive model, because each time you're going to store your history information in this hidden state HT, and you basically, in each time step, you compute this hidden state HT by combining the current information and your previous history. Right, so this is the current information xt and your previous history ht minus 1, and you kind of combine them together, and this is your hidden state, and you can compute this hidden state ht recursively in each time steps. And an important thing about RNN is that it has a weight sharing mechanism. It's actually very similar to convolutional neural network. It just behaves in a different way. In RNN weight sharing, you have these weight matrices W, X, H, and WHH. So these matrices, they are shared across different time steps. So here, when you're computing HT, you're using these weight matrices. But when you're computing HT plus 1, you're also going to use the same set of weight matrices. So this is weight sharing. And after computing these hidden states HT, you can then use whatever output layer you want to compute the predicted output. Right? For example, if you want to predict next word, then you can simply go through another linear layer followed by a softmax to predict the probability of each word in the vocabulary in your next token in the sentence. Right? So this is the vanilla version of RNN. So the vanilla version of RNN has a lot of problems, but it's general enough to give us some kind of intuition of what RNN are like. And we say that RNN, they actually have different variants and different settings. We have one-to-one setting, one-to-many setting, many-to-one, many-to-many. Right? And I've had two kinds of many-to-many. One is to use an encoder-decoder architecture. We're still going to talk about this in this lecture. And the other one is that one has a one-to-one mapping version of the many-to-many. Okay. So this is the vanilla RNN. And since the vanilla RNN has a lot of problems, right? It has gradient vanishing and gradient explosion problems. We briefly talked about this during free forwarding, because you have weight sharing, and then you need to multiply it by the same weight matches many times if you have a long sequences. Therefore, it's very easy to get gradient explosion. Not gradient, just your hidden layer is going to explode if you use ReLU, because ReLU is unbounded. So this is why you need some activation function that's not ReLU, that are bounded, and you can use sigmoid or hyperbolic tangent or tangent H. So this is why you see sigmoid and tangent H so often in RNN architectures. And so this is the feed forwarding. You need to prevent explosion. And the backprop, you have explosion and vanishing problem as well. So we briefly talked about this in the previous lecture. So the key is, if you're still using vanilla RNN, then it's actually very difficult to prevent gradient explosion and gradient vanishing. And this is why we need some gated version of RNN. And in the last lecture, we talk about a very specific variant of gated RNN, which is long short-term memory model, or LSTM. So let's have a very, very brief review of what LSTM is and how the computation proceeds. So in LSTM, you have 3 gates. So first of all, you're gonna combine your previous history, ht-1, and your current state, xt, to compute the value of these 3 gates. Right? So all these gates, they have values between 0 and 1. This is why they're called gates, right? Because they're either open or closed. But they're soft gates, so they're actually real values between 0 and 1. Okay. So you have these 3 gates, and then since in LSTM you distinguish between cell states and hidden states. Then the cell state is trying to store all the history information, and hidden state is part of the history information that's relevant to the current prediction. So in order to compute cell states, you will need to compute a candidate cell first. So the candidate cell is also computed by combining your current state and your previous hidden states. So this is the middle one in here, and then you can compute your final cell states by combining your previous cell states and your current candidate cell states. And the way to combine it is to use the 2 gates that you have computed before, right? You compute the forget gate here, right? And you compute the input gate in here, right? So these gates becomes the weights that you will use to combine the previous cell states and the candidate cell state to get your current, most up-to-date cell states. So this is the cell states. So far we have almost finished everything. The last computation you need is the hidden state. We say that the hidden state is going to be part of the cell states. Therefore, we're going to compute the hidden states as part of the cell states. So, and which part, right? Which part of the cell states, that depends on your output gate. So this output gate, each element in the output gate control what part of the cell state do you want to keep or do you want to delete. Right? So this circle with a dot inside of it is a element-wise product of matrices. Okay. So this is LSTM. And before we move on, just to make sure, any question on this LSTM part? Question remaining? I guess in some sense it's similar, but attention usually they're normalized to 1, right? You have the total attention of 1 and try to distribute the attention into different part of the input. But for get gate and input gate, they do not normalize to 1. So that's really the only thing that's different. But yeah, at a high level they're similar. Yeah. And in the next variants of RNN, we're going to have something that's more similar to attention. Yeah, because the 2 gates actually adds up to 1, so that's more similar. Yeah, good question. So more question? Where the hidden states goes to? So you mean after you compute this HT? After you compute this HT, this hidden states goes to 2 things. The first thing is that if you want to predict the next words, right? You can use the hidden states and go through some linear layer and softmax, and then you predict the next words. This is the first path. The second path is that this hidden state is used to compute the next cell, right? You can see that this is to compute HT, you need HT minus 1. Right. So it goes to the next cell. Yeah. Cool. Any more questions? Okay. So this is LSTM, and this is actually going to be part of the optional homework. And again, optional homework is optional. You don't have to do it, but if you do it, you get extra credit. So LSTM is going to be part of the optional homework where you're going to implement these computations that I have just talked about yourself and use it to, for example, performing natural, we call it neural translation. Yeah. Okay, so the LSTM seems quite complicated. So people have been thinking about, is there a way that we can simplify LSTM? And several years ago, maybe 7 or 8 years ago, there is a variant of LSTM that tries to simplify it, and they're actually able to simplify it without sacrificing much performance. And the performance between these new variants and this LSTM is usually very close. Sometimes it's kind of like slightly decrease the performance, but the saving of memory is usually worth it. So in this new variants, you have, instead of having 3 gates, you actually have only 2 gates. Right? In LSTM, you have input, forget, output gates. In this new variants, we call it gated recurrent units. It only has 2 gates. So these 2 gates, they are reset gate and update gate. And another difference is that in LSTM, we try to distinguish from cell states and hidden states. Right? We have the C, right, and we have the H. And in this GRU, or gated recurrent units, we only have the H. Right? They basically combine. They basically combine C and H. So this is GRU. Let's go through the computation briefly one by one. To compute these 2 gates, right, we have this reset gate, RT, and we have this update gate, ZT. Right? So they're actually very similar. To compute each gate, you're going to use your current state, XT, and your previous history. Right? And they each will go through some kind of linear transformation and go through some kind of sigmoid. So this sigmoid makes sure that the output is between 0 and 1. So this is to compute reset gate, and then you have similar way to compute the update gate. Right? So these are matrices, okay? And then, the key thing in GRU is that they first compute the proposal hidden states, and then compute the final hidden states. So the proposal hidden state is computed by, it's kind of expected though, right? You want to compute your current hidden states, then of course you're going to need to combine your current input state, XT, and your previous hidden states, right? That's expected. What's different is that they have this reset gate here to control what part of the previous history you would like to keep when you're computing your next proposal hidden states. So this is the key thing that is different. After this previous history, go through the gate. So part of it will go through the gate, part of it will be deleted, right? And then it will get linearly transformed by another weight matrix, WHH. And then of course you're going to go through some nonlinear activation. So this is the proposal. This is the proposal hidden states. We call it HT tilde here. And then, so you can see that so far we have only used one of the gates, right? This is the reset gate. So where is the other gate? The other gate is update gate. It's used in the final equation here. So it's used to compute your final hidden states. And the final hidden state is the weighted average. So now it's not weighted sum, it's weighted average. It's weighted average of your previous hidden states and your current proposal states. Now you can see that these two part of the weights, right? This one, they actually add up to 1, right? Because this is ZT and this is 1 minus ZT. Okay. So this gate this update gate control what part of basically the weights you want to assign in your previous history or in your current proposal state. Okay. And it might be helpful to consider a very special case here where you have a reset gate that is all zero. Like, let's say that this reset gate is a matrix of all zeros. In this case, all your previous history will get canceled out, right? So this whole thing will become zero. Right? This whole thing will become zero. That means your HT tilde would only be related to XT. Right? And let's say that not only RT is zero, ZT is also zero. If ZT is also zero, then all your previous history will not affect your current hidden states. And ZT is zero. If ZT is zero, then this one is this matrix is all one, right? And you can see that if ZT and RT they are both zero, then your hidden state basically forget everything that you have memorized before, and your hidden state will only consider your current input, right? That's a very special case, but that gives you an intuition of why how these gates work. So it's kind of have this reset mechanism to help your gated RNN to so basically you need to be able to forget something, right, in order to remember something else, right? So this is kind of the intuition that this GRU gives the model the choice to forget things that are irrelevant and only keep the things that are relevant. And in this case, the things that is really important can be remembered for a long time. So by a long time, I mean a very, very long sequences. Even after a very, very long sequences, you can still keep this information instead of getting washed out by all these recurrent operations. Okay. And this is the intuition about how this gating mechanism works. Before I move on to the next slide, any questions? You mean only use the proposal and do not use this update? You can do it, but I'm sure the authors have tried it before. I can give you two things. One thing is that if you only use the proposal state, that's still quite similar to the original RNN. The only difference is the reset gate here, right? And the second thing is there is actually a special case where you only use the proposal state, right? Because if you keep the proposal state and then you keep this, let's say that's the same, right? So if you keep this proposal state and let's say that your Z is zero, if your Z is zero, then that's exactly what you said. Right? So this model is kind of like a generalized version of what you said and provides more flexibility. It can kind of roll back to what you said if needed, but if the model needs more complexity, it can also do it. Yeah. I think it's mostly just to solve this gradient vanishing problem. We're going to analyze it in the next few slides. So adding this gating mechanism kind of helps with this gradient vanishing and gradient explosion. basically it introduced some kind of shortcuts for you to for the gradient computation. Yeah, you're going to see this later in the next few slides. That's a good question. Okay. Any more questions? So this is GRU. All right. So let's give it another pass. So in GRU, you have different, like LSTM, right? You have different steps. So the first step, you're going to compute all the gates. So in the first step, you're going to compute the this reset gate and update gate, right? And then you're going to compute the proposal hidden states. Right? The proposal hidden states is computed by combining the current input and your previous history, right? Here and here. And you can actually kind of compare your proposal hidden state computation and the vanilla RNN. So this is the vanilla RNN. Right? And the only difference is really that you have this reset gate to control what part of the previous history needs to pass or not. All the others, they're actually identical. That this part is the only thing that's different between the vanilla and our current proposal hidden state computation. Okay. And so this is the first step. You compute the gates and compute the proposal states. And then you're going to use this proposal states, right? Like what we have shown in this figure. Right? This is the reset gate and this is the update gate. Right? And you're going to compute a weighted average of your previous hidden states and your current proposal state. To pass this figure, let's see if we can pass this figure. So basically, you have Z in here, right? You have Z in here, and this is 1 minus Z. So 1 minus Z, and this part here is your previous, it's your current proposal state, right? In here is your current proposal state. So you are multiplying 1 minus Z and your proposal state. So in here, right, this is your 1 minus proposal state, right? Okay. And the other thing that's going to be using the update gate. So here, the update gate goes from here to here, right? So this is still the update gate, and you have this previous hidden state ht minus 1. So they're gonna be used to compute the element-wise product. And here, at this point, this is gonna be Z element-wise product h. All right, this is gonna be h t minus 1. Right, and then you're gonna add them up. Right, this is gonna add them up to your final hidden states. So this is the computational graph, and we all know that this computational graph is really what's happening under the hood of, for example, PyTorch and TensorFlow, because this will help the program to compute the feed-forward path and then through the backpropagation to compute the gradient of the parameters. Right. So this is actually very important. So this is GRU. And we have a final comparison of GRU and LSTM. So if you compare GRU and LSTM, you can see that GRU has only 2 gates. It has a reset gate, our matrix R, right? And we have the update gate, our matrix Z there. So it only has 2 gates, while LSTM has 3 gates. It has input gate, output gate, and forget gates. And in terms of proposal computation, our GRU compute the proposal hidden states using an additional reset gate on the previous history. And LCM's proposal computation is simpler. It's just simply combine the previous history and the current input. Right. And the state update, GRU, you can see that GRU use weighted average, not weighted sum, weighted average to make sure that these two things, the weight of these two two terms to add up, they actually sum up to 1. And LSTM is different. LSTM just have a forget gate multiplied by t minus 1 and plus the input gate minus, multiply by your proposal cell state. So there's no guarantee that this forget gate and this input gate is going to sum up to 1. Okay. So these are the main difference between GRU and LSTM. Now we can see that in terms of computational cost, GRU is going to be saving some computation, right? And in terms of memory cost, because you have fewer gates, right? First of all, you have fewer gates. Second, GRU doesn't really distinguish between cell states and hidden states, so it saves even more memory. Therefore, you can see that GRU actually saves some computation and GPU memories, and they still achieve kind of similar performance. So that's so GRU is something that we can try if you have limited memory and you still want good performance. Okay. Any questions so far? All right, I guess it's clear enough. So now we're going to very briefly talk about how gated recurrent unit or GRU deals with this vanishing gradient problem. Okay. So if you recall our GRU, right, this is the key step when you are trying to update your hidden state. Right? You have this Z here. This is the update gate, right? And Y minus Z here. And now in this equation, we're gonna rewrite ZT as UT. Basically, ZT and UT in this slide, they refer to the same thing. Right? U stands for update. Okay. So to compute HT, you're gonna compute a weighted sum of your current. Okay, sorry. So this is actually something slightly different. So UT is gonna be 1 minus, according to this equation, UT is gonna be 1 minus ZT. Okay. UT is gonna be 1 minus ZT. And then you can rewrite your GRU hidden state update using this equation. And we can see that this is just the UT times the proposal state plus 1 minus UT times your previous history, right, your previous state. So this whole thing is very, very long line here is your previous state, okay, HT minus 1. Right. And you can see some patterns here, and you can actually expand all these terms. And after you expand all these terms, you can see that you can actually compute HT using a sum of a lot of terms with similar pattern. Why do we say that it's similar patterns? Because you can see that it's always going to be a lot of 1 minus U element-wise product with UT minus 1, and then times the proposal state. Right? So this one is 0. Basically, it's the product of zeros because there's no 1 minus t, right? 1 minus UT. It's going to be 0. This one, 0. There's no 1 minus t, 1 minus UT here, right? And the second term you have one term that is 1 minus UT, and in the third term you have two terms that is 1 minus UT. Right? So they all have this very, very similar pattern. Therefore, you can write all these terms, kind of group them, and rewrite them using this equation up here. So that's, for example, that this second term, or any one of these terms can be rewritten into this form. And then you can see that if you try to compute the gradient, of one h with respect to another h further into the history, then this gradient is actually it's simply just the product of a bunch of gates. Right? Then in this case, you can think of it as that your GRU is actually providing some kind of shortcut for you to compute the gradient from HT to H further into the history. Right? And compared to our previous vanilla RNN, right? This is our previous vanilla RNN. In our previous vanilla RNN, you need to actually go through the product of many matrices, and they are going to be the same matrices. So this is going to be harder, right? Because it's going to be the same matrices, and you multiply by a lot of times. It's very, very easy for these matches to get gradient vanishing or gradient explosion. But in here, the gates are much more flexible. It provides it's much easier to compute. So this, at a high level, we try to introduce a shortcut, right? And then it kind of significantly alleviates the problem of gradient vanishing. Okay, so this is a very high level analysis. Hope it makes sense. Okay. And any questions so far? Before we introduce some more advanced technique of gated recurrent units and LSTM. Okay, so no question. Let's move on. So one typical issue that you're going to run into when you use like GRU or LSTM is when you have extremely long sequences. If you have extremely long sequences, then usually you're going to run out of memory. That you have a sequence of 1,000 words, or even if you're modeling a book you have millions of words, and it's actually very difficult to do feed forward and backprop, right? Using just one shot. And the reason is that when you're training this RNN, right, you need to do feed forward and backprop, right? And during this feed forward and backprop, you need to keep all these middle states, right? You need to keep all these middle intermediate states in the memory, and you need to save all the gradient computation in the memory. So that's actually gonna cause a lot of GPU memory, right? And one thing, one approach to alleviate this problem is that you can actually use what we call truncated BPTT. So BPTT stands for backpropagation through time. So why is it truncated? Why is it truncated? It's truncated because it allows you to truncate a long sequence into multiple small sequences, and you can update your LSTM or GRU one small sequence at a time. So concretely, the way you do this is that, let's say that you have a sequence of 6 words, right? And let's say that for now 6 words is too much for your very, very small GPU memory, and we want to cut it into two small sequences, each consists of 3 words. Okay? And in this case, you're gonna do the feed forwarding using these first 3 words, right? Using these first 3 words, and then you can compute your error and do your backpropagation, right? And after everything is finished, you're gonna only keep this final state. So it's just one vector, right? It's just one vector, and you're gonna clean out everything clean out everything else in your GPU memory. So this part no longer costs any GPU memory. You only keep the final state, and you use this final state as your initial state to your second small stage, right? In the second stage, you're gonna handle this second small sequence with 3 words, right? You're gonna handle this small sequence with 3 words, and you're gonna use this previous final state as your initial state, and you do feed forwarding to get your error, right? And then you do backprop to compute the gradient of your parameter, and then you update your parameter. So in this way, you actually using this truncated BPTT, you're actually allowed to save the memory cost by half, right? Because each time you only need to handle a smaller sequence with only a length of 3, instead of handling this long sequence with a length of 6 all at once. Right? So this is truncated BPTT. It's surprisingly commonly used in the early days of GRU, like maybe 5 years ago or something, because natural language words might seem to cost less, little memory for you, but if you are handling videos, each time step you're going to have a 1000 by 1000 high resolution images. Then if you're modeling videos, these kind of memory, like GPU memory, will very, very quickly run out. That is why usually you are going to need this truncated BPTT if you want to model videos as well. So this is truncated BPTT. Question or not? Mm-hmm. Oh, that's the disadvantage of this problem, because in the truncated BPT you do not review the first part. So that's the kind of the kind of information that you lose to trade off for this efficiency. So you update the first part and you keep only the final states, and then you forget everything else, and then you start with the second part, right? And after your second part, you do not go back to your first part. No. I'm sorry? It remembers your short-term memory. It also remembers your long-term memory, because you have the final states, right? The final state in LSTM, this final state is going to be both the cell state and the hidden state. So it keeps everything, basically, keeps everything that's needed. So it does remember long-term memory, and when you need this, that usually means that even a small sequence, it's actually very, very long enough. It's like 1,000 words in the book. That's already more than qualified as long-term memory. But then again, this final state is already kind of transmitted to the next state, so the memory actually it's kept inside the states already. Yeah. The loss is, this is only for many to many settings. Right? If you're right, right? This example is a simple example where you have many to many mapping, and for each input step, you're going to have an immediate error for you to backpropagate. Right? Yeah, that's a good question. If your loss function is calculated at the last, then yes, you will need to rebuild. You will actually need to rebuild your first part, and it's doable, right? Because when you're computing your next part, you can still compute your gradient of the loss with respect to your initial states, right? And the gradient, you can go back to your first part. Yeah. I'm sorry, the size what? Or you mean how do you cut this long sequence? Usually you just cut it in a way that it just fits your memory. You don't want to cut it into pieces that is too small in size. Yeah, the longer the better, as long as it fits into the memory. Yeah. questions? Okay, so truncated BPTT, one advanced technique for GRU. The next one would be bidirectional RNN. So by RNN, I mean it can be any RNN. Right? It can be GRU, it can be RSTM, it can be vanilla RNN. And birational means that you actually have, if you think about typical LSTM or GRU, it usually goes in one direction, right? It goes from the start of the sentence to the end of the sentence. But sometimes it's beneficial to go from the end to the start. For example, if you are trying to determine, I don't know, the post tag, right? Determine whether this word is a verb or it's a or it's an object or it's a subject. It might be helpful to look on both sides, right? Look to the left to the words and look to the right of the words. So in this case, it's beneficial to have two LSTM, right? You have two LSTM first. So this is the first LSTM. In the first LSTM, you're going to go in this direction, right? And you can see that in the first LSTM, this is your input, right? You're going to send your input into your LSTM, and this is each LSTM cell. So each of them is going to compute the HT, and each cell, right? Each orange circle here is going to compute your HT and CT, okay? And it goes from the start of the sentence to the end of the sentence. And you have a second LSTM. This is your second LSTM. Your second LSTM, it also takes the same input, right? Takes the same input, right? But it goes from the end of the sentence to the start of the sentence. It goes in this direction. And these two LSTM, they're actually parallel, right? They don't interact with each other. They interact with each other only in the end, only when after this LSTM, after they are computed, after the LSTM are computed, you have all these output hidden states, right? You have this HT, right? Let's say that this one, you have this HT, and the second LSTM, you also have this HT, right? You're going to concatenate these two HTs in here, right? And then you're going to feed forward, for example, if you have only one label for each sequence, then for example, you can just pick your last time step, and this last time step is actually going to concatenate two HTs, and then you're going to go through some fully connected layers and self-maps to do your classification task, right? So this is bidirectional RNN. So it can be bidirectional LSTM, bidirectional GRU, so on and so forth. Yeah. And it's very, very commonly used. Questions? Okay. The next one is deep RNN. So you can see that all we have talked about is simply one layer of RNN, right? By one layer, I mean you have only one. It's one sequence going from start to the end, right? And in each time step in the sequence, you only go through one layer of linear and nonlinear, and then you can basically get your hidden states, HT. But how about stacking multiple RNNs? For example, in here you have, so S are the inputs, right? S are the inputs, and then you have this first layer. This is your first layer RNN. Right? In the first layer RNN, you can compute your HT. Right? This is your HT. Right? And then you can actually use these computed HT as the input to your second RNN. Right? And you can compute everything in the same way. And by doing this, we can actually stack multiple layers of RNN, right? And then you can stack as many layers as you want. And let's say that you stack for L layers, And after these L layers, for each hidden state, for example H3, you then can go through some linear layers or fully connected layer or multiple fully connected layer to get your output states. So this is the output. This is basically output. Right? This is the output that you're gonna, for example, if you want to do classification, then you're gonna use this output vector to go through some softmax, and this is gonna be your classification probability. Okay. So this is deep RNN. You can stack many layers, and this is also very commonly used. And in PyTorch or in TensorFlow, you can initialize an RNN, and one of the parameters for you to choose is how many layers of RNN you would like to initialize. So it's actually quite convenient. Yeah, but in the homework, you're going to implement this yourself, so not so convenient in the homework, just to help you understand the inner workings of this RNN. Any questions so far for this deep RNN? Okay, it's quite straightforward. And another thing that we need to mention is the encoder-decoder architecture. So this is more or less the same as what we have discussed before, right? We have multiple modes, multiple settings for RNN, and one of them is many-to-many, and right here, right? And this is basically the encoder-decoder architecture, right? The encoder, you input. Let's say that this red one is your input sentence that you want to translate. Let's say that this is an English sentence, and then you encode it into some representation, and then you go through another layer, another RNN, or let's call it the decoder RNN, to decode it into a French sentence. Right? So this is the encoder-decoder architecture. Okay. And it's very commonly used. Let's say that this is encoder, and this encoder will encode "Hello World," an English sentence, right? And then it's gonna. So this is RNN, right? RNN has this last time step of hidden states. After you have this last time step of hidden states, it's gonna go through a decoder RNN, right? So this part is gonna be a decoder RNN. The decoder RNN is gonna decode a French sentence for you. So VOS is the beginning of the sentence. It's kind of like a placeholder, and then this RNN cell is gonna take your previous, basically your hidden state from your English sentence and the beginning of sentence embedding, which is trainable, to translate the first word, right, of the French sentence. After you do this, the RNN is gonna take your first word as input, right, and then your previous state to generate the second word of the input, so on and so forth, until this RNN generate an end of sentence token. So this is also another token specified for the end of sentence, also learnable. Right? So this is a typical example of we call it sequence-to-sequence model. Right? You have sequence as an input, and then you have sequence as an output, and you have the encoder RNN, you have decoder RNN. Okay. Another example is weather forecast, right? So, like I said, each time step you can have one image. Right? Let's say that you have the previous 40 minutes of radar images to see the cloud density on the sky, right? And you would like to predict the cloud map for the next hour, right? So this is also can be implemented using the encoder-decoder architecture, right? You can encode the previous 1 hour of images. Basically, it's a video, right? And then you can use a decoder to predict the video in the next hour, right? And you can also combine this encoder-decoder architecture and deep RNN. Right? So this is going to be the deep RNN. Well, you can see that this deep RNN, basically, you have this. This is input, right? This is time step 1, time step 2, and you go through one layer of RNN, and another layer of RNN, and another layer of RNN. Right? So So this is the encoder. This is basically the deep RNN architecture. And if you look at this part, it's actually the encoder-decoder architecture. Right? So this is the encoder, and this encoder, you have this final state. The final state will be sent into the decoder RNN, right? The decoder RNN is going to decode something. And the decoder RNN also has multiple layers. Therefore, the decoder itself is going to be a deep RNN, right? It's going to go through multiple layers, and then finally predict the first time step and the fourth time step. So this is, you're given the first two time steps, and you want to predict the next two time steps. Right? So this is deep RNN plus encoder-decoder architecture. Okay. Questions so far? Okay. And maybe, let me see, one last thing. One last thing is you can also, so we only talk about natural language so far, right? We can use this LSTM to model sentences, model languages. And one good thing about modeling languages is that everything can be completed in using fully connected layers, right? So it's just simple matrix multiplication, because each word, you can first transform it into a vector or an embedding, and then everything can be done in a fully connected manner. But when you're modeling videos, each time step it's now a image, right? So image, you have spatial information. Right? So it's like going from MLP, multi-layer perceptron, to convolutional neural network. This typical LSTM is a fully connected, it's an MLP version of LSTM. And in order to handle videos, right? In videos, each time step has spatial information. Therefore, you need to have a convolutional version of LSTM. Therefore, in this convolutional version of LSTM, you would need to basically modify every linear operation, linear transformation. You're going to change it into a convolutional operation. For example, to compute the input gate, right, you would need to multiply a weight matrix with your input state, right? And this part, if this x here is no longer a vector, and now if x here is actually now an images, so a vector is just a first order tensor, right? It's just one-dimensional matrix, or you can say that. But if S is now an image is a matrix now. So to handle a matrix, you will actually need to replace this linear operation, this linear transformation, with a convolutional operation. So now if ST is an image, you're going to replace this matrix vector multiplication with a convolutional layer. So this now becomes a convolutional layer. And this W here is our convolutional kernel, right? And basically, you're going to replace everything that's matrix vector multiplication with a convolutional operation, right? And this happens both in the computation of gate. It also happens in the computation of the cells, right? In the computation of the cells, even when you're going from the previous history, right? For example, to compute the current cell, you will need the previous history, right? Previous hidden state, and you're going to multiply this by a weight matrix. Now you're going to replace it, right? Because now the hidden state is also a feature map, right? It's a feature map. It's a kind of like a matrix with spatial information. Therefore, you will need to replace this matrix vector multiplication in the original LSTM with a convolutional layer. So this is the convolutional operation. This star stands for convolution, okay? And with this simple modification, you can actually go from modeling sentences or translating sentences to predicting videos. Basically, you have a input video, and using this one, you can have a encoder-decoder architecture to predict the next few frames of the video. So this is an example where you predict a video where you have multiple digit moving, or moving analysis data set, right? It can capture kind of different granularity of movement. We have a deep architecture. So in the first layers, it kind of try to model very subtle movement in each pixel, and the second layer it models the larger scale, right? The larger scale movement, and the highest layer it models the largest scale movement of each digit. Okay. So this is the end of our RNN. But before we move on to the next part of this class, I'd like to see if there's no questions or not. Questions so far in the RNN part? So we talk about vanilla RNN. We say that it's easily susceptible to gradient explosion, gradient vanishing, and then we talk about GRU, LSTM, and we talk about several advanced techniques of GRU and LSTM. Okay. Questions so far or no questions? Okay. Now we can safely move to our next part. Okay. Interesting. So we're gonna have this. Okay, so the next part of this class is gonna be attention mechanism. So we're not only going to talk about attention mechanism, we're also going to talk about the application of attention mechanism to different architectures, including transformer, GPT, BERT, something like that. Okay. And this is actually why attention mechanism is useful, because if you're familiar with ChatGPT, so that's kind of a very, very advanced application of attention mechanism, because it's based on GPT, and GPT is based on transformer, which is based on attention mechanism. Okay. So what's attention mechanism? At a high level, attention mechanism tries to implement this functionality of selection and attend inside a neural network architecture. So for example, in machine translation, if we want to translate a French sentence to an English sentence, right? And we call this the source sentence, and this is the target sentence. And when you're generating each word in your target sentence, you're generating each target word. Each target word is actually gonna be corresponding to some of the words in the source sentence, right? For example, when you're translating this French sentence to this English sentence of hello world, this hello actually corresponds to bonjour here in the first sentence, in the French sentence here, right? And the world actually mostly corresponds to the third word in the French sentence. So there is this kind of attention or selection or operation that needs to be modeled when you're doing machine translation. And the question is whether we can model it using a differentiable neural network architecture. And the answer is that we can, and which is what we're going to talk about in this lecture. But before we move on, let's take a look at another example of translating. I think it's translating an English sentence to a French sentence. Right? You can see that when it's translating the English sentence on the top to a French sentence, at the bottom, each word in target sentence, it actually corresponds to different part of the English sentence, right? And this is an example of attention mechanism, right? And so let's talk about this attention mechanism a little bit more formally. So the attention mechanism, it consists of two components, or maybe three components. So when you think about attention mechanism, you have, first of all, you have a memory, and this memory, it consists of n key value pairs. So we have this k in each of these pairs is going to be a key, which is, for example, let's bring it up. So this is K1 is the first key, right? V1 is the first value. So each key corresponds to one value, and each key is actually a d-dimensional vector. Value is also a d-dimensional vector, but it's capital D. So they can be different in different dimensions. Okay. So this is a memory. Right? It's very similar to a database, right? You have a key and some value. And then you have a query. The query has to be in the same dimension with the key. Okay? Then basically, what you're trying to do is that given a query, I'm gonna search in the memory for the key that is similar to the query, and then I'm gonna output something. Okay. So in the simplest setting, it would be given the query, I'm gonna search in the memory for the most similar key, and then we're gonna output the value corresponding to this key, right? That's the value. But this is a non-differentiable operation, right? Because this is a hard operation that you just pick one. Top one memory, but attention, if you want this operation to be kind of differentiable, you need a kind of a soft operation. A soft operation, that means given a query, you're going to output a vector that is going to be the weighted average of your n values, basically. So how do you this attention mechanism tries to tell you how do you compute these weights. So here, given a query, the output would be a weighted average of these n values. So how do you compute the weight, right, when you're computing this weighted average? So that's what attention mechanism tries to figure out. And the key thing here is that the query and the key usually have the same shape, because that kind of gives you more convenience when you're computing the similarity between your query and the key. Okay? And more formally, so let's say that we're given a query. Let's say that we have query Q, and how do we compute the output? We first compute n attention score. Basically, we compute n attention score by comparing the query here to each of your keys. So we have n keys, right? So basically, you're gonna have n attention scores. You have this AI, right? So basically, you're gonna have A1, A2, all the way to AN, and there will be different ways to compute this attention score. For example, you can take the inner product, right? You can take the inner product between the Q and your KI, and this can be your attention score. There will be other ways. We're going to talk about this later. But after you compute this attention score, remember we're trying to figure out the weight and use the weight to compute the weighted average. And the weight has to sum up to 1, right? Therefore, we need to normalize this attention score such that it will be guaranteed to sum up to 1. And to do this, you need a softmax operation. So for each key, given a query, for each key you're going to have an attention score, right? And then you're going to go through a softmax layer to normalize it. After you're going through the softmax layer, you're going to have another n values, right? B1 all the way to Bn, and if you sum these n values up, it's going to be 1, right? And then you can safely use these n values as the weight to compute the weighted average of all the values. So this is the weighted average of all the values. It's a summation of n terms, right? It should be something here, right? Capital N, and each of the terms is going to be Bi times Vi. Okay? So this is going to be the output of your attention mechanism. Any questions so far? Okay, no question? So if you look at this figure, so this is going to be your query, and this is going to be your key. Let's say that you have 3 keys, right? And they both will go to this attention mechanism, and this attention mechanism will give you the weight, right? You give it we call it attention weight. So this weight will be, for example, this will be B1, and this will be B2, right? So on and so forth. This will be B3, right? And correspondingly, because you have 3 keys here, and these 3 keys corresponds to these 3 values here, right? These 3 values, then you're going to B1 times B1 times V1, B2 times V2, and B3 times V3, and then you're going to add them up. Okay, add them up and get this up. Okay. So there are multiple ways to compute this attention score. Right? One way is use dot product. You can use, for example, given a query and given a key, you simply compute the dot product, right, or the inner product between these 2 vectors. One problem, potential issue of computing this dot product is that this dot product may be may scale with the length of this product, right? If you the length of this vector, if your vector is too long, then most probably the dot product will also be very large, but we don't want, right? We actually don't want this kind of correlation between the dimension and the dot product result. So we would like to divide the dot product by the square root of d, which d basically is the dimension of the key or the query. So we try to minimize this nuisance influence of the dimension d. So we need to we'll basically try to divide it with a square root of d. Okay. And this is one key step. And the other point I would like to mention is that this is just one key and one query, right? And this operation can, of course, extend to multiple key and multiple query. It's exactly the same thing. It's just that we can write it in a more complex form using the matrix, using matrix calculation or matrix computation. Right? Let's say that you have m queries. Right? You have m queries, then and each query you have d dimension. Right? Then you're going to have a query matrix of n by d. Right? And let's say that you have n keys, and each key is a d-dimensional vector. Then you have a key matrix, right, of the size of n by d. Okay. And then you can basically replace this inner product with a matrix product. Right. After you do this, basically you're going to have a n by n matrix, n by n matrix, divided again by the square root of d. So this n by n matrix gives you the attention score for each pair of query and each pair of query and keys. Okay. So this is dot product attention, and similarly, we can consider another scenario where, for example, if key, query, and values, if they are in different dimensions. In particular, if the key and query, if they're in different dimensions, what can you do? What you can do is that the naive idea, of course, is just to project both the query and keys into the same dimension. For example, dimension projected into each dimension, right? And then you can do this inner product thing. Right? Just use a matrix. Use a matrix to project it into each dimension. Right? So for the keys, you use this weight matrix WK. For queries, you use a weight matrix of WQ. Okay. So both of these metrics, they are learnable weight in the neural network. Okay. So after doing this, they're in the same dimension. Therefore, you can just simply use the inner product to compute the attention score. Right? And alternatively, you can do it another way, which is actually a more popular way, is you first transform them into the same dimension, right? Using these two matrices, and then you add them up. You add them up and go through some kind of nonlinear and linear operation. And note that this U here is another learnable vector for you. You can actually think of this as very similar to concatenate the key queries, right? And go through some kind of hidden layer perceptron to compute your attention score. And this hidden layer perceptron can be learned in a data-driven way. Okay? So this is another way to compute the attention score. Now, of course, after you compute the attention score, you still need to go through a softmax layer to normalize it. Okay. Any questions so far? The most of the operations are quite straightforward. Okay, so this is the building block of everything that we're going to talk about next. So this is the attention mechanism. Attention mechanism is just a data-driven way of computing the weighted average. Right? So we're going to take a 10-minute break, and we can resume at 1:35. Okay. So can we wait for a second? Okay, let's get back to our class. So we talk about different ways of computing attention scores. Right? We have dot product, easier version, and we have NLP attention, which is the slightly more complicated version. So now we are ready to think about something more practical. So why do we need this attention mechanism, and how does it get incorporated into a actual neural network architecture to do some actual tasks, right? And one example is you can use this kind of attention mechanism inside of a sequence-to-sequence model to do machine translation. So this echoes our previous example, right? When you're doing machine translation, you can each target word actually correspond to some of the source word. So by target word, I mean the language you would like to translate to, right? The source word is the original language, right? So let's say that in here you have a source sentence, for example, English, right? And then you would like to translate it into French. So this is the process of translating to French. So the English sentence is going to be S1, S2 all the way to ST. So it's T words. Right, and the French sentence is going to be Y1 all the way to, for example, YT. Right. So let's say that your model is going to generate the translated French sentence, one word at a time. Right? And when generating each word, it's going to look back at the previous words it generates, and it's also going to look at the source sentence to see which word in the English sentence it's going to be related when I'm generating the next French word. So this is very much similar to what a human translator would do, right? It's going to look at the source sentence and look at what I have written, and then to decide what's the next French word I'm going to write. So concretely, let's say that you already, let's say that at this time step, you already generate this word, YT, YI minus 1, and it's currently in the process of figuring out what the next word, YI, should be. And to generate YI, it needs to go through these 4 steps. So now let's talk about these 4 steps, one at a time, okay? And first of all, you will need to see that this is, we're going to have a bidirectional RNN model to process our source sentence. So this is our source sentence, our English sentence. Right? This English sentence is going to go through an RNN architecture. Right? This RNN architecture is going to give you, for each word, it's going to give you a corresponding H. Right? It's going to give you a corresponding H. Right? So this H is going to be used to compute everything that follows. Okay. So here you have the input. So input is your English sentence. Output is going to be our French sentence. And remember, in our attention mechanism, we have the query, key, and value. Right. So what's the query at this time? The query is actually our current state. So this output, right? So when you're generating your French words, you're actually using an RNN as well. So this query is going to be your previous hidden state. So this previous hidden state, because H is already used here, so and then in this decoder, and then we're going to use S to denote the hidden states in the decoder RNN. Okay, so this S, I minus 1 is your previous hidden states. Right? So this previous hidden state is going to be used as our query. This S, I minus 1, basically it contains every information. Basically, it contains information up to this time step about what you have written, right? What the translator have written in the French sentence. Right? So this is going to be your query. And then we have query, we have key, so what's going to be the key? The key here is going to be our, for each of the English words, we're going to have an H, right? For example, this is H1, H2, and H3, right? So this H is going to be our key. So we're going to use this H as a key to compute an attention score for each of the English words. So this EIJ is going to be the attention score we computed for each word, right? So J is the IJ, right? So basically, for example, EJ EI1 is going to be the attention score for the first word in the English sentence, right? So EI2 is going to be the attention score where in the current attention score for the second word. Okay. So this is the attention score, and then you're going to normalize it to get the attention weight, right? Such that it's going to add up to 1. So the attention weight is going to be alpha, and you're going to use softmax, right? You can see that the numerator is the exponential of EIJ, right? And the denominator, you simply add up all the terms. Basically go through different J here, right? Go through different J here to add up all the terms, such that everything can be normalized properly. So T sub S is here, right? So this is basically the T here. T sub S is basically the number of words in your source sentence. Okay, so this is the normalized attention weight, and then you can compute the context. So what's the context? The context is something that's gonna contain what's important in the source sentence that's gonna be related to the generation of your next word. So you compute the context. The context is basically the output of our attention layer now, right? The context will be the weighted sum of all the H's, right? So the weight will be our attention. So the weight here, weight will be our attention computed in the previous step, right? And the value still will, and in here you can see that the value and the key they're actually the same, right? The value is also going to be the H from this encoder RNN, right? And you use this context. This is CI, so CI is here, right? And then you're going to combine this CI and your previous generated words, YI minus 1, and your previous state, SI minus 1. You're going to combine them and go through some layers, right? Go through some linear, nonlinear operations, basically the model of your choice. And then you can update your hidden states. So this is your new hidden states. So after you have this new hidden states, what you can do is, for example, you can go through some layers of, so you have this SI, right? And then you can go through some layers, fully connected layers, and then you can go through some kind of softmax, right? And then you can predict the next words, basically. The softmax can give you the probability of each word in the vocabulary in your next word, right? Of the current sentences. So this is the attention mechanism incorporated into the sequence-to-sequence model. And this is one of the steps, right? This is one of the steps. Right? You compute SI, and then you go through several layers and softmax to generate this next word, and then you can repeat this process to generate each word one at a time until you complete your translation. Right? Any questions so far? before we move to a more concrete example. Okay, so you can see that this is a relatively complex architecture, right? You have a encoder RNN at the bottom, and then you have a decoder RNN on the top. So to give you more intuition, let's have a more concrete example. So let's say that we are at step 4. At step 4, we are just starting to generate the 4th French word from the English sentences, right? And what's going to be the query? The query is going to be here, right? Let's say that the query is a vector of 4 dimensions, right? In here, and we have H1, H2, H3, right? So H1, H2, H3, for example. Right? And so what's next? What's next is that we're going to compute the attention score, right? So basically, this is simply you can think of it as it's actually assuming your source sentence has only 3 words, right? So you have only H1, H2, and H3, and then you're going to compute. You can compute your attention score for these 3 H's, right? And the attention score, let's say that it's 13, 9, and 9. Okay, so this is going to be the EIJ, right? The attention score, the EIJ in here. Right? Okay, and then you're going to normalize it, right? You're going to go through the softmax to normalize it, and it becomes something like this. And this is our alpha IJ, right? And then we're going to use this attention weight, and along with all these H, right? We're going to compute the weighted average of all these H's, right? And this is going to be the weighted sum or weighted average of this values vector, right? And then you can compute the contact vector. So this is the CI in here, right before you generate the SI. So this is a more concrete example. Okay. Any questions so far? How do you get the key value? Good question. Here, the key is equal to the value. So you have a key query. Or how do you calculate it? You get it from your encoder RNN. Right. So everything is string end to end. You have an encoder RNN. Right, this is your encoder RNN, and you have a decoder RNN on the top, right? And everything is string end to end. So you're actually simultaneously training the encoder RNN that gets you this H, and you're also simultaneously training the decoder RNN that tells you how to basically compute the SI from the context CI. You mean the input? You mean in this input layer? Yeah, at the very beginning, this input is a one-hot vector, right? And it's going to go through one embedding layer to get some kind of corresponding embedding for this word. And this embedding layer can be learned end-to-end along with this network. You can also use some kind of pre-trained embedding as well. That's also okay. Does it mean what? Empirically, my experience is that it doesn't really matter that much. So usually you pre-train everything from scratch. That's okay. Yeah. Cool. That's a good question. And of course, if you have very, very limited data, then it might help. If you have very, very limited data, yeah. But if you have enough data, that shouldn't make too much difference. Cool. Any more questions? Okay, so this is attention mechanism for sequence-to-sequence model. And of course, you can have a deep version of this attention plus sequence to sequence model. Right? You have in the encoder RNN, you can have multiple layers, right? And in the decoding layer, you can also have in the decoding RNN, you can also have multiple RNN layers. Right? So here, this is the source. This is the source, and then you're going to go through multiple RNN layers, and you have this attention layer, right? So this attention layer, and this is the target. The target actually, it's basically the something that gives you the y, right? The y I minus 1, something like this. And go through the embedding and go through some recurrent layers, right? And that gives you your current. So this one, yeah. This here is actually your S I minus 1, right? S I minus 1. Right? So one question for you is, if you can understand this figure, then one question is why is there 2 arrows in here? Exactly. Yeah. So here is the keys and values, because the keys and the values are the same. Therefore, it has 2 branches, right? And so this is the keys, and this is the values, right? And the S here will serve as the queries, right? They all go through these attention layers, and these attention layers will spit up some the context vector, right? The CI here, right? The CI here will go through the will go as the input of the RNN, right? The CI will go for input of RNN. So basically, everything is very natural and consistent with this figure. Okay. So this is the deep version of the sequence-to-sequence model, and we have this another example. So you have this encoder, right? You can see that encoder RNN, and then you have a decoder RNN to use the attention mechanism to generate one word at a time, right? And when it's generating one word at a time, it basically combines the context from the source sentence and the previous state in the decoder RNN, right? Okay, let's play one more time. You see that you have the attention part, right? Okay. You have the attention part, and have this previous hidden state part. Okay. So this is the natural language, called machine translation, and you can see that in the machine translation, your input is a sequence of words, and your output is also a sequence of words. Therefore, it's kind of natural to use a encoder RNN and an encoder and a decoder RNN, right? But what if you have another task? Let's say that you want a image captioning task. Given an image, I would like to automatically generate a caption for the image. Then at this time, this image is actually not a sequence, right? Usually it's not a sequence. Right? It's a 2x2 matrix, right? So how are we gonna use this attention mechanism, and along with a decoder RNN to generate a caption for the image? The way to do this is intuitively you can think of it as we are actually replacing all these H's, right? All this H here with feature map, right? With some kind of feature map from this image, but everything remains the same, right? Everything remains the same. Even the decoder RNN and the attention mechanism, they remains the same. The only difference is that when computing the H, we no longer use we actually no longer use the RNN anymore. We use directly the feature map computing from our convolutional neural networks. So that's really the only difference. So we can go through the neural network computation here. First of all, you're going to encode an image to a feature map, right? Let's say that it's a 14 by 14 feature map. and the number of channels is going to be D. So you can kind of see that it now becomes a it now becomes, I think it's 196, right? It now becomes 196 vectors, right? 196 vectors, and each vector is going to have D dimensions, right? So that becomes 196H vectors for you, and this is the 196 key and values for the decoder RNN to attend to, right? So we have 196 vectors here, right? As I said, each feature vector of dimension D in the feature map is going to be used as the value to attend, right? And the key is the same as the value. And then everything's the same. Right? We have the previous hidden state of the target RNN, right? It's going to be used as a query. So basically, this S I minus 1, right? It's going to be used as a query, same as before, right? And the remaining step is basically the same. Right? So basically, you're gonna generate. For example, you're gonna, and this is an example. Right? Let's say that you just generated the word bird, and when you're generating, before you're generating the next word, you're gonna look at each feature map, each hidden state. Let me see. Each key and values, right? So each of these 196 vectors corresponds to the information of each different patches in the image, right? So basically, this decoder RNN is going to choose which area of this image to attend to when it's generating the next word, right? And you can kind of expect that the model is going to attend to mostly the these area, right? This area where you have the wings of the bird when it's generating the word flying here. So this is attention mechanism used in an image to sequence model. So for more natural modeling, right, you're going to replace the encoder RNN with a encoder CNN, and everything remains the same. And you can kind of see this pattern of replacing different blocks of the whole architecture, such that it's going to be more suitable for different types of data. Right? So this is our image to sequence. Before I move on, make sure there's no questions so far. Okay. So the next one will be self-attention. So the motivation of self-attention is trying to, you can see that so far all these models, when we're trying to generate sequences, it all involves RNN. So sequence learning without RNN is something that we want to think about when we use self-attention. So if you compare CNN and RNN, you can see that CNN has an advantage, which is it's easy to parallelize, right? Because in CNN, you can apply the same convolutional kernel to different part of the image, right, or different part of the feature. You can apply it in parallel, which is very computationally efficient because GPUs, they are very good at doing this. They're very good at parallelly computing different part of the equation. But the disadvantage of RNN is that it's difficult for disadvantage of CNN is that it cannot capture the variable length sequence dependency. Right? Because CNN, it takes the image as a whole, and then it will go through many layers, and then at the top you try to concatenate everything and go through some fully connected layers. It does not really explicitly handle this sequential dependency. But if you look at RNN, RNN is actually very good for long-range dependency and variable length sequential information because it takes one word at a time, right? And it has a weight sharing mechanism to ensure that when you process the first word, it's going to be using the same way as it processed the 100th word. So this is good for sequence modeling, but this is also its advantage actually. Its disadvantage actually because RNN needs to go take one word at a time, then it's actually very difficult for within sequence parallelism. If you have a sequence of, let's say you have a sequence of 100 words, then you will need to go through 100 steps to compute just one sequence, right? That's going to be very, very long time, right? And it's actually very difficult to parallelize it. And one question to ask is that can we kind of combine the best of both worlds? Can we have a model that can handle variable length sequential information and also good at parallelism, such that the computation is fast enough? And the answer is self-attention. Self-attention can easily do both. It has easy parallelization. It can handle good long-term dependency, and it can handle variable length. And the same set of model, right? For example, you can learn your self-attention model in very short sentences, but it can be readily used on a data set with longer sequences, no problem, and vice versa. So this is the high-level motivation of why we need self-attention. Okay. And another motivation, kind of like a thought experiment, is that for now, our attention mechanism operates on the assumption that we have the query and a key and then we have a value, right? But what if we don't have the query? Right? What if you have only a set of encodings provided and that's it? So you don't have the queries. How are you gonna do it? And the answer is that you can actually, let's say that you are given a very short sentence. This is a very short sentence with 2 words, thinking machines. So there's 2 words, you have 2 embeddings, right? This is your 2 embeddings. Right? So that's all you have. Let's say that's all you have. And how do you do attention mechanism to get to your next layer? Because you don't have, we know that these can be used as key and values, right? But where is the query? The one thing you can do is that you can imagine that you have some kind of matrix, weight matrix that you're going to learn in the process. And let's say that you're going to multiply your embedding by let's say a query weight matrix. And we assume that after this multiplication, it's going to give you the query. Right? And if you multiply this embedding with another matrix, let's call it key weight matrix, then you're going to get the corresponding keys. And if you multiply it with a value weight matrix, you're going to get the corresponding value. Okay? So this is why it's called self-attention, because it's basically generating the query, key, and values by itself. Right? And after you do this, right, you can do similar things for the second word. Right? Second word you can generate the queries, generate the keys, generate the value. Right? It's very, very simple. And after you have all these keys, queries, and values, and everything would be very straightforward, right? You have so self-attention. So what's the input and output of self-attention? So this is actually the key motivation. What's the input and output? The input of this self-attention is going to, because you have 2 words, right? And the input will be 2 vectors, right? And we also want the output. We want the output to be also two vectors. So how are you going to achieve this using attention mechanism? The way to do this is that we already talked about the first 3 steps. Right? We generate the keys, queries, and values using some weight matrices to learn. And then to compute this first output vectors, what are we going to do is that we're going to use this Q1, so this is the query generated for the first words, right? And we're going to compute the attention score using this query and using the keys from these two words, right? So this is the attention score for the first word, turns out to be 112, and this is the attention word for the second word, right? This is K2, turns out to be 1996. Right? And again, because we are using the attention mechanism, we're going to divide it. Let's say that you have let's say the dimension here is 64 dimensions. Then you're going to be divided by the square root of D, right? So you're going to divide it by 8. So after divided by 8, you're going to have 14 and 12, and then you're going to normalize it. You're going to normalize it using softmax. So after normalizing, this is your attention weight. So 0.88 and 0.12, okay? And then you can use this weight to compute the weighted average of these two value vectors. Okay? You can this one multiply by this one, and this one multiply by this one, right? And you add them up. After you add them up, you get the final output Z1 for your first word or for your first token. Right? So this is self-attention to compute your first word. Right? And you can do similar things. You can do similar things for Z2. The only difference is that when you're computing Z2, you will need to use Q2 as your queries, and everything else is the same. Okay? So this is the self-attention layer. I guess it's still very straightforward, right? Just generate key, query, and values on the fly, and then you use it to compute the next layer. Okay. Any question so far? Oh, sorry. Oh, how this query key value are generated? So back to this slide. Sorry. So let's say that you have this is two words, right? This is two. We can use something consistent to this example. Let's say that you have two words, and this is going to be your embedding. Let me see. This is S1, this is S2, right? So this is before you compute the weight, compute the query key and values, right? And to generate the query, you can multiply this X, right? You can multiply this X with a matrix of size 4 by 3, for example. 4 by 3. And that's gonna give you a vector of 3 dimensions, right? And that's gonna be your query. And this weight matrix, we call it the query weight matrix, WQ. It can be learned from the data because everything is end-to-end, right? You compute it, and you train it, you get the loss, and you backprop. So this is the Q, and you're going to use the same x1. So this is your x1, right? You're going to use the same x1 and multiply it by another matrix. So this matrix is WK. So this is going to be the key weight matrix, right? And that will give you another 3-dimensional vector, right? This 3-dimensional vector is your key, right? K1, and this one is Q1, right? And you can do similar things for the value. Right? So this is like how we describe the computation of one convolutional layer, right? You use this as input, and you compute everything, and you get the output of this current layer, right? And ultimately, we will discuss how you can enforce how you can use some kind of loss function to compute some loss. And then you can use this loss to do backpropagation. And after your backpropagation, you can compute the gradient of W, right? And good question. We're going to talk about this in this lecture, maybe 10 slides after that. Right? So for now, we're talking about the model part, and we will soon get to the objective function part and learning part. Okay. So now we're just talking about how do you get through this one layer of self-attention. Yeah. Okay, so this is the self-attention part. And you can see that this is just computing this output one token or one word at a time, right? We can actually do it all together for both words using a matrix formulation, right? Remember, in the previous slides, we talked about when we're computing the attention score, right? This is the vector version. We can also have a matrix version to simultaneously compute the attention score for n queries and m keys, right? Just using this equation. So here is very, very similar, right? Because we have two words, right? Then we have two words. That means we're going to have two keys and two values, two keys and two queries, right? Then we can use the same thing, use the same equation to compute a 2x2 matrix, which is going to be the attention score for each pair of query and keys. Okay. So the way to do this is that let's say that you have two words, right? Therefore, each word embedding is a 4-dimensional vector. Therefore, you have two words. You have two. You're going to have a 2x4 matrix, right? And then you're going to multiply this 2x4 matrix with a query weight matrix. So this query weight matrix is 4 by 3. Okay, it's 4 by 3. Then after you do this, you're going to get 2 by 3. So this 2 by 3, the first row is going to be the query for the first word, right? And the second row is going to be the query for the second word, right? And you're going to do similar things to get the key matrix, and the similar things to get the value matrix. Now you can finally use this equation to compute the we call it attention score matrix. So this attention score matrix, basically you will multiply this Q matrix and K matrix, right? And multiply by all this, right? And then you're going to go through some kind of softmax layer, and then you're going to multiply by the value, and that finally gives you the W. So to give you more intuition, right? You can see that this, after you multiply this Q and K, right, and doing the softmax, you're going to get a 2x2 matrix. So this 2x2 matrix corresponds to these two words, right? Because you have two words, therefore you have two queries, and you have two keys. Therefore, you're going to have a 2x2. You're going to have a 2x2 matrix. And basically, what this says is that you're going to use this value. You're going to use this value as the weight of your first row. Right? You're going to multiply this one with the first row plus this one with the second row. And this will give you here. This will give you the first row. So this is exactly what's happening in here, right? In here we compute the weighted average of two B's to get your final Z, right? And here you're also computing the weighted average of these two B's, right, to get your final Z1, right? And the attention weight is right here. So this is just a matrix way of expressing everything. Any questions so far? Is it necessary to what, sorry? To compute? I see. So you're asking, is it necessary to compute this attention weight of all the pairs, right? The answer is it's actually it is necessary, right? Because you can see this is a 2x2 example. When you're computing Z1, right, you're already using the first row of this attention matrix, right? And when you're computing this Z2, the second row, you're going to be using these two, right? So every entry is actually necessary, right? There's no waste. And that's a good question because it actually touches one major disadvantage of self-attention. And the disadvantage is that it takes quadratic time to the length of the sentence. Right? If your sentence is very long, for example, 200 words, then the cost of this computation for just one pass is going to be 200 by 200. So that's going to be very, very expensive, actually. And that's part of the reason why usually these kind of models do not handle too many words at a time. Okay. Does it answer your question? Any more questions? Okay, so this is self-attention, right? And you can see that this is only one attention head. Right? So for each, when you're computing Z1, you have only one set of weights, right? You have only one set of weights to compute the weighted average. And we can actually have multiple attention heads. Basically, you can have multiple sets of attention, multiple sets of attention weights to compute a different version of weighted sum, and then we can combine together. So this is one way of kind of making the network more complex, or kind of increase the network capacity in self-attention layer. Okay, and the way to do this, let's go through it one step by step. Okay, so this is going to be your original input. You have two words, and then you go through some embedding layer. The embedding layer is, you can think of it as just a table, right? This is the word thinking. Therefore, the embedding, the four-dimensional embedding corresponding to the thinking is this four-dimensional vector. So it's just a lookup table, right? And this is the embedding of each word, and then you can compute your Z for your first head. So this is exactly the same. This is exactly the same as what we have been doing here, right? Because you can see that the input is a 2 by 4 matrix. The output is a 2 by 3 matrix, right? The output is a 2 by 3 matrix. This is exactly the same. Right? And the parameter here, the parameter to learn in this attention head is a Q matrix, K matrix, and V matrix, right? So this is the first head. The first head gives you a 2 by 3 matrix, and then you can go through the second head. This is the second attention head. In the second attention head, you're going to use a different set of weight matrix, right? This is W1Q, W1Q, W1K, and W1B. And this will give you a different set of query key values, right? And it will also give you a different set of attention weight, of course, and it will give you a different result for Z. So this is Z1, right? So in the first head, you get Z0. In the second head, you get Z1. And let's say that you have 8 heads, okay? If you have 8 heads, then altogether, you're going to get 8 of these 2 by 3 matrix. So altogether, you're going to have, and then in each in each of these Z matrix, right, the first row is going to be for your first word, right, and the second row is going to be your second word, right? The first row for the first word, the second row for the second word, right? Then you can kind of concatenate them together, right, in a column-wise manner, and you get this. So this is a 2 by 24 matrix, right? 2 by 24 matrix. So because you have 8 hats, therefore at the end of this operation, for each word, you're going to have 24 entries, right? You're going to have 24 entries, but this is too much, right? Because you have a lot. Originally you have only 4 dimensions, right? Now you have 8 hats, and it will suddenly go up to 24 dimensions. Therefore, you need to multiply it with another matrix. This is a 24 by 4 matrix to kind of reduce the dimension back to 4. Right? So you multiply this 2 by 4 matrix with a 24 2 by 24 matrix with a 24 by 4 matrix, and that gives you a 2 by 4 matrix. Right? So this is your Z. Okay, so this is your Z, your final Z for your multi-hat attention. And in transformer model, we usually gonna use this Z and go through more nonlinearity. So this would be several layers of fully connected layer and rattle in here. So this FFN stands for feed-forward network, okay? And then that's going to give you your final R. This is one complete layer of self-attention, okay? Any questions so far? Oh, you mean different W, right? Yeah, this is a good question. So you can see this is just computation of one layer, right? And the way you learn it is simply, again, we're going to talk about the loss function, right? At the end of the day, you're going to have some loss function, and compute the loss, and you can backprop, and it's going to automatically compute the gradient for all these W's, and then you can update the W's. Does it answer your question? From W, how do you compute that? Oh, from WO, how do you compute that? Yeah, so here you have, remember for each hat, right? For each hat you have a 2 by 3 matrix, right? And you have 8 hats. Then you can combine all these small matrices together, and this gives you this large matrix, right? And then you multiply this matrix with this matrix, then you get a 2 by 4 matrix. Does it make sense? Cool. You mean the final Z? It actually, usually, that depends on your hyperparameter choice, right? Usually you would like to keep them similar across different layers, because this is just one layer of self-attention. You're gonna repeat this block for many times, so you don't want to change too much. But it's a parameter for you to choose. Right? Yeah, exactly. Yeah. Cool. Why is it a better approach than multiplying? see your point. So you're asking, this is multi-hat attention, right? And why is it better than just have, a big hat, right? It's like you, I see your point. So, but in a big hat, however large your hat is, right? It always generate one set of attention weight. Right? This set of attention weight is going to be a set of scalar value. So ultimately, it's going to attend to one thing. Right? It's going to concentrate its attention to one thing. But sometimes it's not enough. Sometimes it will be beneficial to concentrate its attention on multiple areas of the sentence. We're going to see an example later. Yeah. I'm sure the people who do this, they try like different parameter configuration, right, and then figure out that this is better than just having a very big hat. But it's a trade-off, and it's a parameter to tune, right? Because you cannot infinitely increase your hat, the number of hats, right? Yeah. Any questions so far? Other questions? Many weight metrics, why not just train them? We need these many weight metrics because we need multiple hats, right? If you have only one weight matrix, then you have the best weight. You're referring to these matrices, right? If you have only one set of matrix, then you have only one hat basically, because all the hats will look the same, right? Then ultimately you're asking the same question basically. Why not just use one hat? Yeah, but empirically it gives better result, and you can see in the later example that sometimes it's beneficial to attend to multiple things. Okay, we're going to talk about this later, but now let's see. Maybe just go through this slide and then we can talk. I can answer your question. Okay, so we talk about one layer of self-attention, right? This one layer of self-attention, your input is X, right? And your output is R. You can actually stack multiple layers, right? You can stack multiple. After you get this R, you can use it as input. Right? Have another layer of self-attention. You get another R and have another layer and get another R. And this is exactly what happened in the original transformer model. Right? You have multiple layers. Okay. Now get to the part, right? Why you need multiple hats, because sometimes it's useful to attend to different things. And this is an example where, for example, you're modeling a sentence, and the sentence says something like the animal didn't cross the street because it was too tired, right? And this shows the attention weight for two hats. This is hat 1, this is hat 2. You can see that in the first hat, it concentrates its attention in the animal part, right? And in the second hat, it concentrates on the reason why the animal doesn't really want to cross the street, tired part. So basically, one of the hats concentrates its attention on the subject, and the other hat concentrates on the status of the subject. Right? So in this case, it might be helpful to have multiple hats. And empirically, it also shows important performance improvement. Right? Yeah, this is an example. And we have I think we have the optional, in the optional assignment, we have some some part of it is about a multi-hat transformer to do machine translation. you can try to tune the number of heads, for example, right? If you can, to see if you can have better or worse performance. Okay. Any questions? Before I move to the next part. Okay. So the next part, again, we're going to go back to our old friend, which is sequence-to-sequence model. Right? As a recap, in the sequence-to-sequence model, when we're generating this word, we're going to go through 4 steps. Right? The first step is we're going to compute the attention score for each of this age, right? And then we're going to normalize it, and then we're going to compute the weighted average of all this age using this attention score, and this would be our context vector, CI. And then we're going to combine CI and the previous hidden state, right? Si-1, and our previous generated words to compute our current hidden states. And the current hidden state will, for example, go through some linear layer and salt map to generate our next word. So this is sequence to sequence, okay? And both the encoder and the decoder are RNNs, right? Now we can actually replace both the encoder and decoder with a self-attention layer. So the way to do this is basically you replace all these things with a stack of multiple self-attention layers, and you replace all these things with a stack of decoder self-attention layers. Okay? And to make it more concrete, let's see if we can have a simple example on the blackboard. Okay, so here, now let's say that you have three words. Okay, you have 3 words, and each word have 2-dimensional embedding. So we have 3 words. 3 words, 3. Okay, and so this is your 3 words. And then in these 3 words, it's going to go through many layers, right? Many layers of self-attention layers. It's going to go through many layers of self-attention layers. So in self-attention layer, so this is your X, right? Basically, let's say this is your X. This is X1, and this is X2, and this is X3, right? And I hope you still remember in the self-attention layer, this is, if you have 3 words here, then after your self-attention layer, still you have 3 vectors at the end, right? And this is your, for example, your Z1, your Z2, your Z3, right? Then, this is the top of your encoder. Let's say this is your top of your encoder. After you reach the top of your encoder, what you're going to do? You're going to do the same thing as in the self-attention layer. Just for each of this Z, you're going to multiply this Z with some weight matrix of, let's call it key weight matrix, right? And then you can get your key. Right? You can get your key, so let's call it K1, right? And similarly, you can get your K2 here, and you can get your K3 here. And similarly, you can multiply your Z1, Z2, Z3 by another matrix, WV, and then you get your V1, V2, and V3. Okay? This is at the top of your encoder layer. So this is at the top of the encoder stack. After you do this, you're going to go through the decoder. You're going to go through the decoder. And what does your decoder do? Your decoder tries to generate a new words, right? Tries to generate a new words it's trying to generate. It's basically try to translate this French sentence to English sentence. And let's say that at this point, the decoder has already generated the first word I, right? And it's in the process of generating the second word M. So what it's going to be when it's computing this? Let's say that this word I is actually, we call it YI, we call it YA, Y1, okay? We call it Y1. Let's put it here. Let's call it Y1. And this Y1 will serve as the basis for us to compute the query. Okay, we're gonna use this Y1, and we have this. And Y1 will be multiplied by a matrix. We call it query matrix, right? WQ. This will give you the let's call it Q1. Okay, so the Q1, and then what's going to happen? You can kind of imagine, or you use this Q1 as your query, and just use this Q1 as your query and to compute the weighted average of these three values, right? And what's the weight for this weighted average? The weight for this weighted average is computed using the attention score, right? It's just, for example, you get this Q1 multiplied by K, the inner product between Q1 and K1, you get the first attention score, right? And Q1 and Q2, you get the attention score for the second one. Q1 and K3, right? K3 in here. Then you get the attention score for the third one, right? And then you can basically normalize it using softmax and then compute the weighted average of all these three values. So ultimately, basically you're going to have this alpha 1 times V1, and alpha 1 2 times V2, and alpha 1 3 times V3, right? And this will give you what? This will give you another vector. Right. Let's call it ZY. Let's call it ZY. Okay. This is ZY, and this is one layer. This is one layer of the decoder, right? And you're going to repeat this multiple times. Right? This is ZY. Let's call it ZY1, right? And you're going to repeat another round of this one, and you're going to get your ZY2. I'm going to go through multiple layers of this decoder. And then finally, you can, let's say that finally you get your last layer of ZY, right? Last layer of ZY, let's call it, how many layers? 6 layers. This is your final layer ZY. So this ZY, you're gonna go through a fully connected layer, and then you're gonna go through a softmax layer, right? And then you can predict your next word. Right? This is Y1. You're trying to predict your next word, and you predict your second word, right? So this is the process of using this encoder-decoder stack of self-attention layers for machine translation, for example. Right. Any questions so far? Exactly, yeah. Y1 and Y2 I use again. Now, once you get Y2, then in here you're going to have two vectors, right? And you're going to go through the same process. Right? Questions? Good question. We're gonna see that there is, but this is a simplified version. You're gonna see in your next few slides. Yeah. But now you can assume that there is no attention mechanism between Ys. Yeah. So this is actually in the encoder, right? The encoder it's called self-attention. Right? In the decoder here, it's kind of like cross-attention, right? Because it's kind of cross-referencing x and y. Right? It uses y as query and uses x as key and values. Right? Question? Anyone question? I see some raised hand. How do you what? Oh, the loss function. In this case, the loss function is straightforward, right? Because you can train a model because you already know your next word is what your next word is. You know the ground truth next word, then you can have a cross entropy loss, right? So, for example, you can in one of the iteration you can use this one, the y, you can use y. You can use the ground truth y1 here, but here what you have here is the predicted y2, right? And you have a ground truth y2 here, right? And then you can compute the cross entropy between these two and use it as your loss function. Right? Yeah. Any more questions? Okay, so this is transformer and used in the context of sequence-to-sequence model. And here we mentioned something about position encoding. We're going to talk about this later. Okay. So we have some example here. So this is exactly what I've been talking about with this free word that generates something, and then you generate a key and value, and it spits out I, right? And then use I as input, and it's going to predict M, and then it's going to use IM as input and predict the next word, A, right? So on and so forth, predict the next word, right? Once it predicts end of sentence, then that's the end of the inference process. If not, then the process will go on. Okay. You mean if you stack multiple layers of self-attention, is there anything that inside the attention mechanism? There is some kind of study in here, and because you have multiple layers, right? In the transformer model, usually you have, for example, you have 12 layers, or you have 24 layers. It's somehow a little bit more difficult than you think to analyze the attention, and you also need to choose which layer you want to study on. But there is some empirical study that I think there must be someone who's studying this, and there's also some studies saying that this attention is not really a good way of interpreting how the network tries to reason about the machine translation. But it's still an open field. If you're interested, you can try to search online for some literature. Yeah. Good question. Any more questions? Okay. So this is a already very relatively complete example of how you can use transformer to do neural machine translation, right? And this is going to be related to our optional assignment as well, because in that we're going to build a transformer-based model to do a machine translation. So there's one missing piece, which is positional encoding. So why do we need positional encoding? You can see that our transformer. So if you, by the way, this whole thing, this is basically a transformer model. A transformer model consists of a self-attention encoder and a cross-attention decoder, autoregressive cross-attention decoder. So this is called a transformer. You can see that a transformer actually uses attention, right? And this attention basically consider this input, right? All this input as a set of vectors, right? And it basically ignores the position information, because all that matters for this self-attention layer is the attention itself, right? It doesn't really care about the position information. So, but this is actually a key property for kind of implementing this parallelization, right? Because it treats each position equally, therefore they can apply parallel computing. Right? But the sad thing is that it loses sequential information as well. So to compensate for this, to capture this sequential information, the transformer uses an additional set of vectors. We call it position encoding or positional encoding. And this positional encoding is actually of the same size as the embedding. So by embedding here, we mean, so we can see that we write it as X here, or it can also mean that here, right? Because this positional encoding can also be used in some middle layer. And this positional encoding is going to be exactly the same size as our input sequence matrix as well, right? So, for example, we have this one. You actually have a 3 by 2, right? 3 by 2 matrix, and the positional encoding matrix is going to be a 3 by 2 matrix. Okay? And what's next is that you simply add these two up. Right? You simply add this input sequence matrix and this positional encoding matrix. You do not concatenate them, because if you concatenate them, you kind of double your embedding space. If you double your embedding size, you're going to cost more memory, and you also kind of risk overfitting. Right? Therefore, it seems a better choice is just to directly add them up. Right? So this is position encoding. So this positional encoding matrix, what's the best way to compute? That's the next question. And ultimately, the authors choose to use some kind of sinusoidal functions to compute the positional encoding. To be more concrete, you can see that this is our positional encoding matrix, and each column corresponds to the sequence. Each column corresponds to the sequence in a particular channel, right? So this I here, you can see this I here. I is the length of the sequence. Okay, so each column corresponds to a sequence. Okay, so you can see, each column, yeah, no problem. And if you're in a different column, if you're in a different J, that means you're in a different channel. Right? That means you're in a different channel. Okay. So to compute the value of this positional encoding matrix, they use this equation. Right? This is the full equation. Now with this equation, you can compute any entry in the positional encoding matrix. Now let's take a closer look at these equations. Right? Let's say that we are focusing on a particular column. So we're focusing on a particular J here. Right? Focusing on a particular J here. And by the way, D is the number of dimensions number of channels basically. So the width of this matrix is D. Okay. So if you pick a particular J, right? If you pick a particular J, then if you have different I, let's say that you have different I, that you go from the start of the sequence to the end of the sequence, right? Then that's basically saying that you're kind of moving along a sinusoidal shape, right? And a more concrete example is that let's take the fourth dimension. Like for example, J equals to 4. Right? Then it's something like if you're at the start of the sequence, then the position encoding is here, and as you move along the sequence, it's gonna follow the sinusoidal curve, right, to go up and down, up and down. So this is the fourth dimension. Of course, if you have only one channel, there is gonna be some overlapping, right? For example, if you're gonna have the same value of this position encoding at position 10 as in position here is what is position 50. Right? If you have only one channel, then you're gonna have the same position encoding at 10 and at 50. So that's not good. Therefore, you need multiple channels, right? Basically, that means you need multiple columns here. Right? So in the next dimension, basically in the next channel, you're gonna have a different sinusoidal curve. Right? Now it goes from here all the way to here, so it's slightly different. Right? Then, if you have 512 dimension, that means you're gonna have 512 different sinusoidal curves that serve as your position encoding. Okay? And that can approximately uniquely define the position of each word in the sequence. Okay. Let's pick a particular example. Right? Let's say that you have a particular K, and let's say that K is equal to, I don't know, let's say that you have a K equals to 256 and C equals to 512, right? Then in this case, this one is directly equals to 1, right? And if you pick, let's see, okay, maybe you can do something like, okay, maybe I'm trying to set up an example for you. So let's say that in some dimension, this is a position matrix. This is position encoding matrix, and in one of the column, it would be following this equation, right? This equation corresponds to D equals to 500 and K equals to, for example, 200 and slightly lower than 256. Okay, around this number. Then in this case, if you look at this sequence, it's going to be sine of 0, 9, something like this, right? Times, let's say that we're going from 0 times 0. So this is going to be the first entry, and the second entry is going to be sine 0, 4, 7 times 1, and the third entry is going to be sine 0 times 2, and so on and so forth. Right? So this is going to be your first column, and if you look at the second column, The second column is going to be cosine, same thing, right? Cosine times 0, right? And the second row in the second column is going to be cosine times 6, 7 times 1, right? And similarly, the third row of the second column is going to be 0.9647 times 2, right? So on and so forth. This is the second column, and the third column, right? And the third column is going to be a different frequency. Now, it's going to be sine, right? But it's going to be sine 0.9306 times 1, times 0, right? And the second row is going to be right? So on and so forth. Right? And you have multiple columns, of course. So this is a concrete example of how you compute the positional encoding. Okay. Any questions so far? And in practice, if you want to write the code from scratch, you simply put in this equation. That would be more than suffice. All right, and if you're looking for a visualization of the encoding positional encoding matrix, this is it. You can see that in some of the dimension, in the first few columns. In the first few columns, you can see that this is actually a very large number, right? The large number means you actually have a larger frequency, shorter period, right? So you can see that this number jumps up and down from 1 to -1 pretty quickly, right? In the first few columns, and it gradually gets slower and slower. Right? For example, in this column, it kind of gets slower and slower. And ultimately, if you look at these columns, right, it doesn't really even finish one period. Right? They're all blue. Right? So this actually gives you a visualization of the positional encoding matrix. So this is an example where you have it's not 512 dimension, it's 128 dimension. And with a maximum length of 50. Okay. You can see, so this is the dimension of 50, okay? And this is the dimension of 128. Okay. All right, so this is the positional encoding. Any questions so far? What dimension? Oh, 120. Oh, that's a hyperparameter. Right? 128 means that basically means that your in each of this vector you're gonna have 128 dimensions. Yeah. Okay. It's a hyperparameter, like a hidden dimension in your network. Because your positional encoding has to be of the same size, right? Okay, so this is the positional encoding, and let's quickly finish this one. I think it will be rather quick. So the last missing piece is the mask self-attention. So what's mask self-attention? If you have a self-attention layer, if you have a simple full self-attention layer, let's say that you have three input, right? That's x1, x2, x3, and if you have a self-attention layer to get to your z1, z2, and z3, when you're computing a z1, right? This z1 actually attends to each of these axis, right? And when you're computing Z2, it also attends to each of these axes, right? And same as this Z3, right? Z3 also attends to each of these X1, X2, X3, right? So this is full self-attention. Right? Something is kind of strange here, because when you're computing Z2, and let's say that you're generating your sentences, for example, this one. Right? Let's say that you are translating something, and this is your second word, and we want to generate the words one by one. Right? So we do not want the generation of Z2 to be conditioned on X3. So this is something that's in the future, right? We don't want this to happen. You don't want this to happen, then ideally, you would like something like this. You would like that, again, this is X1, X2, X3, and this is your Z1, Z2, Z3, okay? Z1, Z2, Z3. When you're computing Z2, ideally you want it to only attend to no more than X2, no further than X2 basically. You don't want to attend to X3. So basically, when you are computing the attention, you want to mask the attention to X3, right? And this is exactly what mask attention means. So basically, it's a simple operation. When you're computing the attention, you just directly set the attention to the third vector to 0, and then renormalize it. Right? So this is what mask attention means. And similarly, when you are generating Z1, right, you don't want to attend to X2 and X3, so you just directly attend to X1. Right? So this is mask attention, right? And mask attention is useful in here, right? Because in practice, when you're training this network, when you're doing inference, of course, you're going to do this one by one. But when you're training, the things are actually a little bit tricky here, because to really, we say that one reason we want to use this transformer and self-attention is because we can parallelize it, right? We can parallelize it such that we can train faster. Therefore, one good way to parallelize it is that you put all these y's, so you put all these y's, y1, y2, y3, in here all together in one go, and then you force this network to predict y2, y3, and y4, right, at the on the top. And when the network is predicting y3, right, we don't want it. Sorry, bad example. Let's say that forget about y3. When the network is predicting y2, right, we don't want it to attend to y3 in here, right? So we need this kind of mask self-attention to enforce that when you are predicting y2, it only attends to y1 and y2, right? And this is what mask self-attention does. With this mask self-attention, it would then be possible to train this transformer in parallel for all the words. So this is a high level intuition, and in terms of implementation, it's actually more trickier than you think. And if you're interested, I strongly encourage you to go through the code and go through the optional assignment homework. So this is the mask self-attention, and then this is the last piece. Okay, this is the last piece for our full transformer model. You can see that you have this encoder. This is your encoder, right? And this is your decoder. Right? Encoder, you have multi-head attention, you have app and norm. So that's basically similar to our residual layer, right? Or ResNet, residual connection, right? And you go through a feed-forward network, right? This is the FFN that we mentioned before. Right? you compute the Z here, and then you go through a feed-forward network to get your R, right? And so this is the self-attention layer, and this is the encoder here. And the right-hand side here, you have this decoder, okay? And in the decoder, you can see that in the decoder, you have this cross-attention. So this part is the cross-attention, okay? This part is the cross-attention that we have mentioned in here, right? But you also have this self-attention, which answered the previous question. Right? Before the cross-attention, you actually have this self-attention here. This self-attention, it takes care of the interaction between the Ys itself, right? Between the Ys themselves. So this is the self-attention between the Ys themselves, and the cross-attention up here, it takes care of the interaction between the Ys in here and the X's here. Right? The cross-attention uses Y as query and uses the X's as key and value. Right? Okay, so this is the transformer model. Like you can see that after all of this, it's going to repeat all these blocks many times, and then it's going to go through some linear layers and go through some softness, and then predict the next words, right? And this is a more concrete diagram, and basically says the same thing. Okay, so this is it for today's class. If you are not familiar with some of the details, strongly encourage you to go through the slides again, right? Especially for these few figures, and remember to finish your homework. And we have kind of postponed the deadline to the Monday after the spring break, so that you can have a better rest. Okay, so I guess see you after the spring break.